Hello, my name is Jana Bektas. I am a research assistant at the Communication Networks Institute of the Technical University of Dortmund in Germany, and I will now present you our work entitled SAMUS, Slice-Aware Machine Learning-Based Ultra-Reliable Scheduling in the course of the IEEE ICC Conference 2021 session Network Slicing and Radio Access Networks. My presentation is structured as follows. First, I will give a brief introduction to 5G network slicing and the objective of this work. Then, I will present the utilized methods, including our scheduler prototype and 5G simulation framework. After that, I will move on to the evaluation of our developed framework, and finally, I will summarize this presentation with a conclusion and an outlook to future work. The general topic of this work is the so-called 5G network slicing, which is considered as a key enabler for integrating different service types into a single physical infrastructure. The three main service types are Enhanced Mobile Broadband, or short eMBB for high throughput applications, Ultra-Reliable Low Latency Communication, or uRLLC for applications which require very low latencies, and Massive Machine Type Communication, or short MMTC, for a massive scalability regarding the amount of devices present. Thus, many different key performance indicators, or KPIs, like data rate, latency, or power efficiency, are to be considered by the 5G network and balanced out against each other. One such balance is the latency in uRLLC slices versus the data rate or throughput in eMBB slices, which is the main topic of this work. To further understand the topic of this work, latency components in end-to-end 5G transmissions are depicted in this figure. Latency components exist between user equipment, G node B, the core network, and transport network. In order to comply with the latency requirements of uRLLC slices, the sum of all components must be reduced to the single-digit level, ranging from 5 milliseconds to as low as 1 millisecond. The goal of this work is to develop and compare different trade-off strategies regarding 5G resource scheduling for minimizing T-radio in uRLLC slices while maintaining high throughput in eMBB slices. Later in the presentation, I will detail why these two aspects compete and must be traded off with each other. One utilized method for this approach are the so-called 5G configured grants, which are pre-configured scheduling grants to eliminate scheduling latency due to the instant availability of resources. Thus, future data demands are to be predicted if resource efficiency is to be maximized. In our approach, we utilize the ARIMA method for prediction to implement the SAMUS scheduler prototype and evaluate it with our developed 5G resource grid simulation or 5G RGS framework. In the next slides, I will detail the methods utilized to develop the simulation framework as well as the SAMUS scheduler prototype. The main inputs for our simulation framework are channel conditions and transmission data of the simulated user equipment, which contain transmission times and data amounts. These are fed into the SAMUS scheduler prototype as well as our developed 5G resource grid simulation framework to simulate the data transmission process in the media access layer. As outputs, we obtain the data rates as well as the latencies of all UEs within the different network slices. A detailed description of all modules and their interactions within the simulation framework is provided on this slide. The framework consists of three main modules: the SAMUS scheduler prototype, the 5G RGS simulator, and the prediction module of the SAMUS scheduler. The scheduling module generates configured grants based on a scheduling algorithm which takes network slicing priorities into account, as well as the data traffic prediction, which is calculated by the ARIMA model in the prediction module. The calculated configured grants are then passed on to the simulation module to calculate the data rates and latencies of all generated transmissions by the UEs. Both the prediction and the simulation module use historical traffic demand data to calculate the required configured grants and the resulting UE transmissions. In the next slide, I will detail this process. Here, the starting point is our dataset, which was generated from two real-world sources regarding the two slices simulated later. First, the dataset is divided into 2/3 training dataset and 1/3 validation dataset. The ARIMA model is trained based on the training dataset in order to export the predicted data points to the G node B scheduler. The G node B scheduler calculates the predicted data rate required, which is used to generate the configured grants. The validation dataset is exported to the expected data point, which is then used by the users simulated in the simulation module to generate the actual data rate transmissions. Based on this, the actual data rate required is calculated. To evaluate the prediction quality, this validation dataset is used later in the evaluation scenario. Also, online learning is utilized to further enhance the ARIMA model during the simulation. I will now present you the evaluation scenario and results of our SAMUS framework. The simulation scenario contains three different slices: the smart grid and electric vehicle or EV charging slices with service type uRLLC, as well as the best effort slice with service type eMBB. As you can see, the two uRLLC slices have a higher priority than the best effort slice, which means that our scheduler will consider the high priority slices first when generating traditional or configured scheduling grants. While UEs in the uRLLC slices generate data transmissions based on the validation dataset, the data amount in the best effort slice is set to a constant aggregated throughput of roughly 19 megabits per second, calculated based on the sum capacity of the simulated cell. This ensures that resources are requested constantly in order to stress the whole capacity of the cell and to be able to compare different trade-off strategies. These different trade-off strategies, also depicted as modes, are listed on this slide. In Mode 1, traditional scheduling request and grant mechanisms are used, so configured grants are not activated. Still, network slicing prioritization is available. Mode 2 is divided into Mode 2.1 and 2.2, with the first being fixed configured grants based on the historical average data rate of the slice, so an optimistic approach, whereas the second is based on the historical maximum data rate, hence a pessimistic approach. Mode 3 incorporates ARIMA-based predicted configured grants, where 3.1 does not use over-provisioning and Mode 3.2 over-provisions the predicted resources by 10%. All simulations are conducted in uplink directions, so from UE to G node B, and configured grants, if activated, are only used for the uRLLC slices. The eMBB slice is scheduled traditionally. The results for Mode 1 are presented in this figure. On the x-axis, the simulated time in minutes is depicted, whereas on the y-axis, the average data rate of the slice is shown in megabits per second. The red dotted line represents the maximum channel bandwidth utilization, which would be reached if 40 megabits per second could be transmitted. The solid red line shows the actual channel utilization. The other three solid lines represent the respective data rate in the slices of each color, green being smart grid, blue EV charging, and black best effort. Notice that the scheduler already reduced the best effort data rate by the amount which is needed to transmit the data rate for the two high priority slices. As resources are not granted in a fixed manner but by traditional scheduling request and grant mechanisms, the channel utilization is nearly at the limit, as nearly all resources can be scheduled and are not wasted. However, this will have a negative impact on the latency, which we will see later. In Mode 2.1, two additional dotted lines are depicted for both high priority slices in their respective colors. These indicate the data rate, which is possible due to resources usable based on configured grants. As can be seen, some resources were not scheduled sufficiently by the configured grant mechanism and thus are scheduled by the traditional method. As such, the scheduling delay increases for these packets, which we will also see later. In turn, for the two situations shown here, the resources are sufficient, but also many are unused. This means that the scheduling delay is zero, but some resources are wasted because the configured grants are allocated in a fixed manner. A similar result is obtained in Mode 2.2, where also fixed configured grants are utilized, but now in a pessimistic approach. It can be seen that configured grants are still failing when data rate demand is too dynamic. For the smart grid slice in particular, very high resource wastage is observed, which also corresponds with the very low channel utilization. Here are the results for Mode 3.1, which represent the ARIMA-based predicted configured grant approach without over-provisioning. The data-driven adaptation of the configured grants, which are not fixed anymore, result in a high channel utilization while still providing low latency due to resources being granted beforehand in most situations. However, still some predictions are optimizable. One such optimization method is shown in mode 3.2, where the predicted resources are over-provisioned by 10%. Over-provisioning optimizes the prediction in some cases, however, also more resources are wasted occasionally. A summary is provided on this slide as a depiction of the trade-off between the average received data rate from the requested data rate in the best effort slice in percent on the left y-axis and the mean scheduling latency in the critical slices in milliseconds on the right y-axis for the different modes shown on the x-axis. The dotted line represents the hardest 3GPP end-to-end latency requirement of 5 milliseconds, while the black solid lines show the standard deviation of the result. To better understand the implications, margins for remaining end-to-end latency components, which were described in the introduction, are shown. The best trade-off of high margin for the remaining latency components and the channel utilization is obtained when using the predicted configured grants based on ARIMA, where roughly 80% of the data rate requested by the best effort slice can be transmitted, while still 4.83 milliseconds margin is left for other end-to-end latency components. I will now conclude the presentation with a summary and an outlook on future work. In this work, we developed and evaluated the SAMUS scheduler prototype based on our 5G RGS framework. In this course, we incorporated a realistic network slicing scenario with real-world data tailored for the respective network slices. We then evaluated different trade-off strategies regarding uRLLC latency versus eMBB throughput. There, the ARIMA-based prediction yields the best trade-off. The key takeaways of this work are that data-driven scheduling is essential for high spectral efficiency while minimizing latency for sliced networks, and that the inclusion of the predictability of data transmissions in service level agreements is strongly recommended for 5G network slicing-based operators. For future work, we will include the prediction of channel quality for network slices with high mobility. Also, further machine learning approaches other than ARIMA can be included into SAMUS. Finally, real-world validations of the simulated scenarios can be conducted based on an implementation of the SAMUS prototype on software-defined radio platforms. This concludes my presentations, so thank you very much for your attention. For further questions, you can contact me via email, and for more information on the chair's other scientific activities, you can check out our website or our YouTube channel. Goodbye.